All right, so now what we're going to do is we're going to take that same kind of setup with the attractors and expressions and look at how we might just create discrete elements from them. All right, and the way we're going to do this is we're going to have to move from vectors to planes. And a plane is a two-dimensional space. We can think of a plane as, the top view and the viewports, or the XY plane relative to the world coordinate system. And we can also create custom non-world-oriented planes defined by any number of ways, such as by 3 points, etc. Right, so here's a representation of a plane, right? And specifically, we're going to be looking at creating custom planes. The idea being that if we have a grid, right, or a distribution of elements, that we can use a plane and a custom plane to determine not only the size of those objects, but also how they're being deformed locally, right? So as you can see here, these are not all being deformed kind of just in one direction, like scale in the X direction. They're kind of swelling as you move through the collection of elements. Okay, so this is where we're going to go, and we're going to actually build on the last file. All right, so I'll actually hide that. It's still in the file. All right, so if we open the next file just to see where we're going for discrete, hit open, you can see that up to here, this is all the same stuff. And so we're just going to do a few more operations here at the end. And what we're going to end up with is a collection of objects that we can determine how much they scale and become skinny, but the orientation of those is actually coming back from our set of vectors, right? So the vectors are going to define a local plane. The plane is going to define how these objects scale, and then we're going to get the kind of resulting pattern, right, which doesn't necessarily look like it was generated from a very simple operation, which is just scaling in the X direction, because it's scaling in the local X direction for each one of our planes. Okay, so just so that we keep going with how we have been going before, with the previous exercise, let's actually build it up from the one we did together. So I'm going to take 1-3, reopen that, and then I'll save this as 1-4 attractors plus expressions discrete working. Okay, so the things that I'm going to need here are going to be I'm going to need to keep working with the points and my vectors. So I'm going to turn those previews on, right? Just the vectors and the points, the grid points. Okay. All right. So let's take a look at the first thing, right? Which is that we want to create a polygon at each one of these locations. So if we just have the grid points visible, we want to create a hexagon, or you could create a triangle too, at every one of these point locations. So let's first find our hexagon object. So that's going to be under curve, primitive, polygon, and the polygon is the object that allows us to create a polygon with any number of sides. So 6 is our number of sides for a hexagon, and that's what we're after. So let's go ahead and drop in the polygon object. And this asks for the base plane, the radius of the polygon, so basically how big it is, and the number of segments or sides, which is 6. So we're good to go. We don't have to actually modify that input. So I'm going to take my grid points and connect to P. And again, I get an interesting pattern, but I want them to be non-overlapping. So I'm going to take my spacing and go all the way to S from that original slider. Sorry, not S, but R, the radius. And again, we're at that point where we need to actually give this an expression so that the radius here is half The radius is 1/3 of the spacing. All right, so that gives us a continuous collection of hexagons. There's actually gaps in here, which again, I think is pretty nice for this pattern that we're going to create. And so this is our kind of continuous collection of hexagons that have not been modified in any way, and they're not, nothing's happening to them relative to the attractors. Okay, so I'm actually going to delete this to keep things a little bit cleaner. All right, so this is our polygon object. And the idea here is that we're going to use the attractors and the corresponding vectors that we get from them as a way to influence this grid of hexagons at each hexagon object. All right, so it's kind of a differential grid of resulting hexagons. Okay, the radius input came from the spacing slider all the way at the left, and we have an expression r/3 inside of that input. Okay. There we go. Okay. So what we need to do is we need to create a local plane for each one of these polygon objects. So let's go back to the Vector tab under Plane. Let's start by creating an XY plane at each one of those original point locations. So if we drop the XY plane into the canvas, and again this is going to come from our input grid points, you may get a really messy preview from that. So what's happening is that it's showing us all of the planes as a preview in the viewport. So we may need to go to our display menu and say that the preview plane radius should be smaller, something like 0.25. Okay, so now all my planes are inside of my hexagons, they're not overlapping, so it's a little bit easier to see what's going on. So here are my local planes. Okay, so and they're all right now oriented to the XY plane in the world coordinate system. So what we want to do next is we want to take those planes and we want to orient them relative to the vectors that we found from our attractors, right? So all of these vectors are going to now determine how this plane should be essentially rotated about its center point. So what we're going to do is from these XY planes, we're going to take a look at another option under the Vector Plane tab that allows us to align a plane with a guide vector. So we're going to grab Align Plane. All right, and this takes in the plane to straighten and the straightening guide direction. So the plane is the XY plane, and the guide direction is going to come from our vector, which is out of average, right? So now if I turn the preview off of XY plane, now all of my planes are aligned to my original vectors. Okay, perfect. Planes are aligned. So this is Align Plane. Okay. The next step is that we're going to take this plane, and that's going to help us decide how we're going to scale in the local space of this plane, right? So let's go to the Transform tab, and under Affine, there's something called Scale NU, or Non-Uniform. So this is like Scale 1D or Scale 2D in Rhino commands. So if we grab the Scale NU and drop it in, this is what we're going to use to scale our polygon based on this aligned plane. Now, there's a question about what's the difference between the two objects right here that are aligned plane or aligned planes. The difference is that the base plane is going to get aligned by a different type of input. Here it's going to be aligned by a vector, and here it's going to be aligned by another plane, right? So we don't have another plane to help us align with, so we have to use the first one, which is align plane. Okay, so the scale non-uniform, right? We'll give that a label so that you know where that came from. Scale New York? Nope. Scale non-uniform. Okay, so if you ever find yourself where you've got an example file or an object and you don't know where it came from, one key is that you can hold Control and Alt and click and hold down the object, and it will give you these arrows that show you where that object is located on the tabs. Ooh. Okay, so this asks for the geometry to scale, the base plane for where we want to scale from locally, and then the values, the scale factors in X, Y, and Z. All right, so let's take our P polygon output, and that's going to be our scale in G, the object we want to scale. P is our plane that we want to scale from. And I'm going to turn the previews off of these two so that we can focus on the previews of the scale non-uniform. And now we're going to drop in a slider from params input, number slider. Let's connect that into Y. Okay, so turn some previews off here. Okay, so now all of our objects are scaling based on a local plane, right? And what that does is kind of give us the a field of objects or a pattern of hexagons that are orienting, or what looks like orienting, and scaling based on these attractor points, which of course you can move around in Rhino and get live feedback. Okay, so one more time, the shortcut to finding where objects are on the toolbars. If you select an object and hold Control-Alt and hold it down, it gives you the red arrows and the red circle that describe where that object is. Okay, and of course if we use this slider, which is our scale factor, we can change the kind of characteristic of our polygons that are getting scaled. Okay, while we're here, let's talk about how we could turn this into a file for laser cutting. So really all we would need to do is take all of these objects and put them onto a layer that should probably be called something like cut first. I'll make that layer current in Rhino, and then I'll right-click and bake my object onto the cut first layer, and grouping, that sounds good to me. Hit OK, and now I have those objects on a cut first layer in Rhino. And I'd probably want to have a cut last layer around the outside, just a rectangle to cut it out. And that would get me to having some geometry that I could produce something like this from. Okay, so that's as far as we wanted to go with this file. So if you have any questions, go ahead and drop them in the window. We'll hang out here for a second and address those questions before we move on to another strategy which looks at not how we understand attractors as influencing discrete elements, but how we might have a kind of continuous representation of those attractors through contours. Okay, couple of quick questions. What are we doing with graphed? Graphed is the object that, or the action that allows us to move from points organized in columns to points organized in where each point is on its own list. What that does is that if we were to connect this collection of points directly into the vector 2 point, we have our problem with data matching, right? If there are 23 points in a column and 3 attractor points, the first point's going to find the first attractor, the second point's going to find the second attractor, the third point's going to find the third attractor, and then all the rest will also find the third attractor. So we'll be only registering the difference or the influence of the attractor each cell with one attractor. And that's not what we want. We want each cell to be influenced by all 3 attractors. So what we do is we graph our input points and we leave the attractor points on a list. Therefore, the result of every one of these vector actions of creating the vector from 2 points gives us 1 vector for each one of the attractors starting at our cell. Okay. That's a really good question.